Newton's three laws of motion are fundamental principles in classical mechanics that describe the behavior of objects in motion. These laws provide a framework for understanding how forces affect the motion of objects and are essential for comprehending various physical phenomena. Also known as the law of inertia, Newton's first law states that an object will remain at rest or in uniform motion in a straight line unless acted upon by an external force. This law highlights the concept of inertia, which is the tendency of objects to resist changes in their motion. Newton's second law of motion defines the relationship between force, mass, and acceleration. The law states that the force acting on an object is equal to the mass of the object multiplied by its acceleration, F equals ma. This equation quantifies how the application of force results in changes in an object's motion. Newton's third law of motion states that for every action, there is an equal and opposite reaction. This means that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force back on the first object. This law illustrates the reciprocal nature of forces and is fundamental in understanding interactions between objects.
Newton's laws form the basis of classical mechanics and are crucial for understanding the motion of objects in the physical world. Mastery of these laws allows scientists and engineers to analyze and predict the behavior of systems ranging from simple mechanical devices to complex celestial bodies. Newton formulated his laws of motion in his monumental work Philosophiae Naturalis Principia Mathematica, commonly known as the Principia, published in 1687. This work revolutionized the field of physics and laid the groundwork for modern science. Prior to Newton's work, there was no systematic framework for describing the relationship between forces and motion. Newton's laws provided a mathematical foundation for understanding dynamics and became the cornerstone of classical mechanics. Newton's laws have numerous practical applications in fields such as engineering, aerospace, and sports. They are used to design structures, vehicles, and equipment, as well as to predict and analyze the motion of objects in various scenarios. Newton's laws can be observed in countless everyday situations, from the motion of vehicles on the road to the trajectory of projectiles in sports. Understanding these laws allows individuals to make sense of the physical world around them. In the context of Newton's laws, force is defined as any interaction that causes a change in the motion of an object. Forces can be exerted through direct contact, for example, pushing or pulling, or at a distance, for example, gravitational or electromagnetic forces. Mass is a measure of the amount of matter in an object and is a fundamental property that influences its response to applied forces. According to Newton's second law, the acceleration of an object is inversely proportional to its mass when a constant force is applied. Acceleration is the rate of change of an object's velocity over time and is directly proportional to the force acting on the object, as described by Newton's second law. Acceleration can be positive, increasing velocity, negative, decreasing velocity, or zero, constant velocity. Newton's third law of motion highlights the concept of action and reaction pairs, where the force exerted by one object on another is always met with an equal and opposite force exerted by the second object on the first. This law explains phenomena such as the recoil of firearms and the propulsion of rockets. Numerous examples illustrate the principles of Newton's laws, such as the motion of a ball rolling down a hill, demonstrating the first law, the calculation of the force required to accelerate a car, applying the second law, and the launch of a rocket into space, utilizing the third law. Newton's laws provide the foundation for classical mechanics, which encompasses the study of motion and forces in the physical world. These laws serve as the starting point for understanding more complex phenomena in physics and engineering. Newton's laws are validated through empirical observation and experimentation. Scientists and engineers conduct experiments to measure forces, accelerations, and other variables to confirm the predictions made by Newton's laws and refine our understanding of motion. While Newton's laws accurately describe the behavior of objects at everyday speeds and scales, they break down at very high speeds, near the speed of light, and very small scales, atomic and subatomic levels. In these extreme conditions, the principles of quantum mechanics and Einstein's theory of relativity are required. Despite their revolutionary impact, Newton's laws are not the final word in physics. Subsequent developments, such as quantum mechanics and relativity, have expanded our understanding of the universe and revealed phenomena that cannot be explained within the framework of classical mechanics. Newton's laws of motion represent a monumental achievement in the history of science and have profoundly influenced our understanding of the physical world. His work laid the groundwork for centuries of scientific progress and continues to shape the way we view the universe.
Thanks for watching.